Hi, welcome back, guys. I hope that you tried some of the student practice that I put on my website. But for now, we're going to do applications of exponentials. So a common model for this is y equals f of t is equal to a to the b k t, where a, b, and k are constant and t represents time. If a function f increases, we call it exponential growth. If f decreases, we call it exponential decay. Exponential growth is obviously seen or was seen, it seemed to be trending as like with the COVID-19 graphs that they show on TV. Those are sort of exponential because you kind of expect each person to double or increase by two. You expect everybody to pass it to at least one person, and so you kind of double the population that has the virus. But luckily, it seems like it's getting a little bit better throughout the world. So hopefully it goes away pretty soon. Exponential decay, I think that has to do with like sunlight in water and stuff like that. There's other examples too, but not on off the top of my head. But one place where we find exponential decay, another place, is a chemistry problem. We have the half-life of radium is approximately 1600 years. How much of a 1 gram sample will remain after 1,000 years? So if we use the formula from before, we have a 1 gram sample. So A is 1 gram because that's the initial amount. The half B is actually 1/2. Why? Because this is a half-life. T here is 1,000 because that's how many years are actually passing. And then K is 1600. And so it only, or I'm sorry, K is 1 over 1600. But it only makes sense that it's a fraction because you have to divide 1,000 by 1600 to figure out how much time has allotted. If 1600 years had passed out of the 1600, that would make a full 1, and therefore it would mean that 1/2 life had passed of this initial amount. So let's think about that. When I used to do this in high school and taught myself how to do it, I used to think of it like this. If you're at 0, if no time has passed, you're still at 1 gram. These were the grams. This is the time. If you're at 1 year, then half of that 1 gram exists. So this is a half a gram. Or I'm sorry, if 1,600 years passed, then you're at that. I'm sorry. If 3,200 had passed, half of 1/2 is there, so that's 1/4 of a gram. And then you just keep adding 1,600 years. 4,800. And now you're at 1/8. And so it just keeps getting smaller and smaller. And so with that being said, we know that we have 1,000 years passing. So we're going to need that calculator. So let's use it. We have, let's pull it up. So we had A is 1, so we don't need to enter that, but we have 0.5 raised to the 1,000 divided by 1,600, which is 0.6484. So we can get rid of that. Or we can answer that as that, 0.6484. So this is equal to 0.6484 grams. Now that makes sense because we're somewhere between 1 gram and 1/2 of a gram. And so this seems like a plausible answer for this, and I'm almost positive it is right, so we should be good to go. The next type of problem is light intensity, where I0 is the intensity of light above water, K is the constant that represents the clarity of the water, and X is the distance in surface below. So we have at one location, we have light above the water is 12 lumens. Oops. So that's your I0. We have the constant at 0.6. And we want to know the intensity at 5 meters. So we're going to use that formula. We have 12 times 0.6. Oops, I put the parentheses too close. So times 0.6 to the fifth, because x represents, sorry, this is x is equal to 5 because we said x is the distance in meters below the surface of the water. And this is going to equal the intensity. So if we use the calculator, we're going to do 12 times 0.6 raised to the 5. And we get 0.9331. And so that is the intensity of the water, or I'm sorry, that is the light intensity overall. All right. Then the next one we have is population growth, and we have where K is equal to B minus the birth minus death rate. And so the population of the US is 300 million, so we're just going to use 300. So we have P is equal to 300. We'll know that it's in millions. Assuming an annual birth rate of 19 and 7 per thousand. So we have 19 per thousand minus 7 per thousand, which is 12 per thousand. Predict what it will be in 50 years. So remember, E is a number, and then we have 12 per thousand times 50. 50 goes into 1,000. 50 goes into 50 one time. 50 goes into that, I believe, 20 times. Okay, so this is going to be E. We could just put the numbers in too. So we'll just put the numbers that we're given. We have 300 times E to the 12 divided by 1,000, and then times 50. 546 635 635 640. And so there will be 546 million people, 635,640 people by the end of 50 years. I hope this helps, guys. Make sure that you do the student practice. Just practice this. This is not completely difficult. For the student practice, you may need to pull up the questions from here. I don't remember. I think I put the old ones, because all I did is I asked you a different question based on these same ones we just did. So if you see the same problem we just did on the student practice, just know that you should use the numbers from there, but not do the same problem. Thank you, guys.